My name is Maleeha Arshad and I'm from Fast News Islamabad. My roll number is I236040 and today me and my group members Ajwa Nadeem, roll number I236070 and Hafsa Asim, roll number I236137 will be presenting our digital logic design final project. Our project's name is Digital Voting Machine. I'll now start. Initially, our goal was to build a simple digital voting machine with 3 independent voting booths, one for each candidate. The plan was to focus on accurate vote counting and display. Once we had the basic system up and running, the 3 voting booths, vote counting, and display, we received valuable feedback suggesting that the system should also include a comparator to automatically detect the winner. We took the feedback seriously and started working on the comparator. While we weren't able to fully integrate the comparator section into our physical hardware due to some technical constraints, we did successfully simulate and implement it on Proteus. The simulation accurately compares the vote count and lights up the LED corresponding to the candidate with the highest vote, giving us a complete end-to-end digital voting system in a software environment.
Let me explain how our voting booth actually count the votes and display them on the 7-segment displays. Each voting button is connected to a 98555 timer, which generates a clean pulse every time the push button is pressed. This pulse is then sent to a BCD counter, which drives a 7-segment display to show the vote count. However, since each counter can only count from 0 to 9, we had to cascade 2 counters together for each candidate to be able to count votes beyond 9. So when the first counter reaches 9 and roll over to 0, it sends a carry out pulse to the second counter, effectively incrementing the tens place. This allows us to display counts like 12, 15, or even higher, with first display showing the units digit and the second showing the tens digit. This cascading setup is what makes our vote counting scalable and suitable for larger voting numbers, even with simple digital logic components.
We use the comparator to compare the votes for party A, B, and C. We take the inputs from any 55 timer, which sends a pulse whenever the push button is pressed. The pulse goes to the BCD counter, and the count that will count the votes for each party up to 2 digits. And so we use the two BCD counters the per party. The output of the party A and the B counter goes to the comparator, which will give the output that A is greater than B, A is less than B, and A is equal to B. And we repeat the same comparator for party B versus C and party A versus C. So if A is greater than B and A is also greater than C, so both the LEDs will on, and this their output will be high. And if their output will be high, so in order to announce the winner, we make those outputs the input to the AND gate. So if both the inputs of the AND gate will be high, so its output will be high, and this will announce that the winner is party A. And we repeat the same process for party B and C. Now it's time for the Proteus simulation, and for we can see from here that if we are incrementing, so it is showing that the party A is now greater than B, and it is similarly showing that the party A is greater than B, and party A votes are also greater than C because they are 0. So it is showing that the party A is the winner.
This is the physical implementation of our project. As you can see, it has 3 voting booths, each working independently. Each booth can count up till 99 votes, and after the votes have been casted, you can reset the machine back to 0 so that it can be used again.
This project allowed us to engage deeply with the practical side of digital logic design. Beyond just building a working circuit, we learned how to break down a system into functional blocks, troubleshoot issues at each state, and think critically. Even though We faced hardware limitations, successfully simulating the comparator logic in the Proteus, but could not implement that on the breadboard, taught us the value of flexibility and persistence in engineering projects. Most importantly, this experience gave us the confidence to approach more complex digital systems in the future with a clearer understanding of how hardware logic is built, tested, and refined.